Hello there, and welcome to another video in the How the ByteFrost Works series. Last time, we looked at a simple model of CPU operation and alluded to two other topics: microcodes, the tiny programs that the CPU runs to execute instructions, and the fetch operation, which is the process by which the CPU fetches an instruction from instruction memory and loads it into the instruction register. In this video, we'll look at the fetch operation and how it is implemented in the ByteFrost. Let's begin by examining an abstract view of the fetch operation. There are a few parts that look a bit different, but this is in essence the same diagram that we saw in episode 1. We have the instruction memory, which is labeled here as the program EEPROM. In case you're wondering, an EEPROM is a particular kind of memory that is both non-volatile and programmable. So even if you turn off the ByteFrost, the program EEPROM retains its data and we can easily rewrite its contents, making it a practical medium to store our programs on. We also have the program counter, which keeps track of what the current instruction is in the program EEPROM. The current instruction is stored in the low and high instruction registers. The reason we have two, as you may remember, is due to each instruction being 16 bits long, but each register only being 8 bits long. The current instruction's opcode is sent to the microinstruction EEPROMs to specify to the CPU which instruction we want to execute, and the microinstruction counter keeps track of the current microinstruction in order to run the current instruction's microcode. This counter wasn't shown last time, but it works in essentially the same way as the program counter does, the difference being that it keeps track of the current microinstruction instead of the current instruction. Lastly, we have at the bottom here a box labeled the fetch state machine. This part is what will orchestrate the fetch operation, telling each of the other pieces what to do in order to fetch the current instruction and to get ready to fetch the one after it. For now, we'll treat it as a black box, but after we go through the high-level process of a fetch operation, we'll look at how the fetch state machine works. Okay, let's examine this diagram. Let's assume that we already have some program loaded in our instruction memory, or program EEPROM as it's labeled here. We've already run the first three instructions, meaning we ran instructions 0, 1, and 2, since our program counter is 0 indexed. Now the last microinstruction of the third instruction, instruction 2, is running and sends the PC advanced signal to the fetch state machine. This is a call to fetch the next instruction, instruction 3. Notice that the program counter already has value 3, meaning that it's already pointing at the instruction we want to fetch. Now, as we mentioned earlier, instructions in the ByteFrost instruction set are 16 bits long, but the data output of a program EEPROM is only 8 bits wide. This means that each instruction takes up 2 bytes in the program EEPROM, so we're going to need to read the values of 2 consecutive addresses to fetch our instruction. The first byte of an instruction in memory is the low byte, and the second byte of an instruction in memory is the high byte. Notice that if we were to send the program counter directly to the instruction memory's address, we need to increment the program counter twice every time we'd fetch an instruction, since we'd need to fetch the low byte and then the high byte. This would mean that the program counter won't keep track of only what the current instruction is, but also of whether we're looking at the low or high byte of that instruction. But that information isn't relevant to the program counter. It's only relevant in the fetch operation due to the limitation that we can't read all 16 bits of instruction at once. To alleviate this issue, we don't send the program counter to the address of the program EEPROM directly. Instead, we shift the program counter value once to the left, and the least significant bit comes from the fetch state machine instead. Hence, the fetch state machine keeps track of whether we're looking at the low or high byte of the current instruction, which is much more appropriate. We can see that the program counter stores 3, and when shifted left, this becomes 6. The least significant bit that is sent from the fetch state machine is 0, so the overall address is 6, and so the low byte of instruction 3 is stored in address 6. Okay, so now that we have a correct address for the low byte, we're getting the low byte of the current instruction out of the program EEPROM's data output. We just need to store it in the low instruction register. Both low and high instruction registers receive a value, but the fetch state machine only sends a load enable signal to the low instruction register, so in effect, it is as if we only sent the value to the low instruction register. We're halfway done. We just need to fetch the high byte of the current instruction and store it in the high instruction register. We don't need to change the value of a program counter since it's already pointing at the correct instruction, but we do need to increment the least significant bit of a program EEPROM's address. We do this by having the fetch state machine send a 1 to the least significant bit of a program EEPROM's address, and so the address becomes 2 times 3 plus 1, which is 7. This is the address of the current instruction's high byte, and we store the high byte outputted by the program EEPROM in the high instruction register in the same way as we did for the low instruction register. Now that we've fetched the instruction, we don't need to point to it in instruction memory anymore. Hence, we can increment the program counter to point at the next instruction, instruction 4, so that we'd be ready when the next PC advanced signal arrives to fetch the next instruction. Since we have the current instruction, instruction 3, ready in the instruction registers, we can send its opcode, which is stored in the low instruction register, to the microinstruction EEPROM's address input. This will tell the CPU to execute the current instruction, and we now just need to wait until it finishes doing so. In a future video, we'll go over how the CPU executes the current instruction by examining how this microcode EEPROM works, but for now, we can treat it at a high level as simply running our instruction. Now we can iterate through the microinstructions that comprise the microcode of the current instruction. We can see that each microinstruction's control signals are being sent to the rest of the ByteFrost to execute our instruction. When the CPU finishes executing, a PC advanced signal will be sent to the fetch state machine, which will have us repeat this whole process to fetch the next instruction, instruction 4. So we just saw the abstracted out view of the fetch operation, treating the fetch state machine as a black box. Now we get to go a bit deeper and see how it works behind the scenes. There are 3 parts here labeled by their chip names in the 74LS integrated circuit line. The 2 chips labeled 273 low and 273 high are the low and high instruction registers, and as you can see by the number of flip-flops inside them, they're 8-bit registers. The chip labeled 175 contains 4 flip-flops, but we only need to use 2 of them, specifically flip-flops 2 and 3. Now in the original diagram, the high and low instruction registers were outside of a fetch state machine, so really the entirety of the fetch state machine is just this 175 chip and an extra AND gate we'll see later. Let's go through the process in the same way we did before. We already ran instructions 0, 1, and 2, and are now receiving the PC advanced signal from the last microinstruction of instruction 2. This signal is a value 1 which is sent to D2, the input of a flip-flop labeled 2 in our diagram. As you can see, the current output of flip-flop 2 is a 0, which is sent to act as the least significant bit of a program EEPROM's address input. Hence, right now, the input address to the program EEPROM is 6, as we saw before, and so we're getting the low byte of instruction 3 from the data output of a program EEPROM. Once the next rising clock edge arrives from the main clock of a ByteFrost, the 1 value from the PC advanced signal passes through flip-flop 2 and is sent to the clock input of the low instruction register. This may seem a bit peculiar. In our previous diagram, the fetch state machine sent a load enable signal to the low instruction register, but instead, here it's sending a signal to its clock input. This is actually how we send the load enable signal to the low and high instruction registers. The 273 chips don't actually have load enable inputs, so we used the clock input as a load enable. In fact, it might be more appropriate to say that this acts as a load trigger, since unlike a load enable where you have to wait for the rising clock edge for the value to be updated, as soon as we send this signal to the low instruction register, it creates a rising clock edge which immediately updates the register's value. If you're interested, write a comment below and I'll make a separate video that explains this aspect of the design. For now, however, just know that this is our implementation of how the fetch state machine sends the load enable signal to the low and high instruction registers. In any case, we've now stored the low byte of instruction 3 in the low instruction register, and we can see that the 1 value that we used as a load enable for the low instruction register is also being sent to the least significant bit of the program EEPROM's address input. As the program counter hasn't changed yet, the current input address to the program EEPROM is 7, as we saw before. The next step in our original diagram was to store the high byte of instruction 3 into the high instruction register, but a few things must happen before this can occur. First, we send the output of flip-flop 2 to the input of flip-flop 3. We do this because, after the next rising clock edge, flip-flop 3 will output this 1 value and send it to act as a load enable for the high instruction register, which will cause the high instruction register to store the high byte of instruction 3. Additionally, we send the negated output of flip-flop 2, which, since the output of flip-flop 2 is 1, would right now be 0, to this AND gate here. This AND gate's output acts as a reset signal for the microinstruction counter that we saw in the previous diagram. The idea here is that, since we're going to execute a new instruction, we need to reset the microinstruction counter to 0 so that it points at the first microinstruction in the microcode of the current instruction. The reset for the microinstruction counter is an active low signal, so by sending a 0 input to this AND gate, we are guaranteed that the output will be 0 and that the microinstruction counter will be reset. Finally, we also send the output of flip-flop 2 to the decimal point LED of a program counter display. This is more of a useful debug indicator during single step. When the decimal point LED lights up, we know that we're in the middle of a fetch operation, and so that we haven't yet started to execute the instruction pointed to by the program counter. Now, this may look a bit fishy. We're sending the one output of flip-flop 2 to increment the program counter, but we haven't yet stored the high byte of the current instruction. Won't this move the program EEPROM's address prematurely and store the wrong byte in the high instruction register? No, and the reason for that is that this is a synchronous increment signal, i.e. it's telling the program counter to increment, but it will only do so on the next rising edge of the main clock. Right now, as we mentioned, the input address of the program EEPROM is 7, meaning that the program EEPROM is outputting the current instruction's high byte. Immediately after the rising edge of the clock, flip-flop 3 will output a 1 signal and cause the high instruction register to store the high byte of the current instruction, while at roughly the same time, the program counter will increment. There is an apparent race condition. The high instruction register needs to store the high byte of the current instruction before the program EEPROM's data output changes as a result of the program counter value incrementing. However, it will take much more time for the program EEPROM's data output value to change, so the high instruction register will never lose the race. As a result, we stored the high byte of instruction 3 in the high instruction register and incremented the program counter so that it points at the next instruction, instruction 4. This matches up with our high-level diagram from before. Now, all that's left to do is execute the instruction. We send the opcode of our current instruction from the low instruction register to the microcode EEPROM, which isn't shown here, and the ByteFrost will execute our instruction. When our instruction finishes running, it will send another PC advanced signal and the fetch process will repeat. Now, you might have noticed that we seem to have a fundamental problem. If every instruction loads the next instruction by sending a PC advanced signal when it finishes executing, how do we load the first instruction in our program? Our state diagram has become a chicken and egg dilemma, as it can't get itself started. There are many possible solutions to this, but the one we used is the following. When the ByteFrost is turned on, the program counter and the instruction registers are reset to 0. Hence, the opcode that is initially sent from the instruction registers to the microcode EEPROMs is the opcode 0, or in other words, the opcode for the NOP instruction. You may recall that all the NOP instruction does is send a PC advanced signal. Hence, the first implied instruction that is executed by the ByteFrost is a NOP instruction, which then sends a PC advanced signal to fetch the actual first instruction that is in the instruction memory. And there you have it. We went over a lot in this video, covering both the high and low level explanations of how the fetch operation works. The high and low level diagram animations are part of the ByteFrost documentation PowerPoint, available in the ByteFrost GitHub in the documentation folder, so if you want to explore this topic further, the documentation is available. I also wanted to show you a cool feature in the slide documentation. The slides have been built to be very interactive, so you can click on these arrows to see where they go to, and you can always click on the ByteFrost logo at the bottom right here to go to the main overview of the different components of the ByteFrost. You can click on any of these components to get an overview of how it works. Shout out to my dad, Keidar, who made this incredible documentation of our project. The exact slides that were referenced in this video are indicated in the video description, and if you have any questions, please put a comment down below or create an issue on GitHub. Thank you very much for watching. If you liked this video, please subscribe so that you don't miss future videos.